So I just want to thank everyone for joining this Lunch and Learn about life sciences construction projects presented by Bala Engineers. I'm Jeff Lyons. I'm a project manager with Clemens Construction, and I'm head of their special projects and service division. I actually just finished a lab renovation for UPenn a few months ago at Hill Pavilion, which was a level 3 animal biosafety lab. So Clemens began hosting Lunch and Learns about a year ago. And then this one, we decided to open up the forum to some clients and designers. So over the last few years, there's been a major upward trend in the life sciences construction center. A lot of that has been due to the increased focus on gene therapies, pharmaceutical discoveries, and then of course, different developments in vaccines. So compared to the first half of 2019, construction spending as a whole has gone up 5% in the first half of 2020. With sectors such as hospitality and commercial that are drastically down during that time period, the overall increase was mostly due to the explosion of these life sciences projects. The majority of these life sciences projects are highly specialized. This is due to the need for clean rooms, wet rooms, precise ventilation, air monitoring systems, different types of temperature controlled spaces, and many other aspects. So today we are lucky enough to have some folks from Bala Engineers to give us this presentation, and I'd like to thank them for providing us this opportunity to learn. I'd also like to thank Carol Horn-Penn and Steve Poppert for helping to organize this. So now I'm going to hand it off to Tanya Zacco, who is the marketing manager at Bala.
Thanks so much, Jeff. Hi, everyone, and thanks for joining us today. I am going to quickly introduce our Office to Lab presentation team, starting off with Scott Davis, who has 32 years of experience in mechanical design for life science labs and pharmaceutical research production facilities. We also have Chuck Kensky, who is an executive vice president, and Chuck has over 30 years of experience in managing, engineering, and designing laboratory and mission critical facilities. Lastly is Steve Anastasio, who is the director of our structures practice group, and he has over 12 years of experience in structural design and management. His experience also lies in adaptive reuse and structural renovation projects. The first few slides we have here are your typical AIA housekeeping slides. I do want to make mention that during this presentation, if you have any questions, we thrive on having our presentations interactive, so feel free to unmute yourself and ask, or use the chat feature. And then lastly, I just want to let you know that Carol's going to provide me the registration list after the presentation, and I'm reaching out to each one of you over the next few days individually to confirm that your AIA credit or the certificate you requested has been provided. And if you forgot to provide that information upon registration, you can chat Carol during the presentation, and she'll make sure you're added to it. So I will now hand it over to Chuck.
Thanks. So the learning objectives that you're going to see today is the building infrastructure considerations when evaluating for the lab, the trends that we're seeing in life science market and how they have a direct effect on the planning for the future of life sciences and clients, the infrastructure requirements for labs and how they differ from common existing office spaces infrastructure to the lab, and then architectural and structural implications of converting an office building over to labs, okay? So what the slides that we're actually going to go through are going to be building evaluation. We'll go through the different metrics, how we do some quick planning level strategies, case studies, and some lessons learned. Okay. So the building evaluation. So you're looking, can my building accommodate a lab. So we get these calls from the developers and building owners, and we run down to the building, we take a look at the building. Well, what are we looking for? Well, a number of things. You know, the location of the building. Is it urban, suburban? Do we have parking access? Is it in a neighborhood of housing? Is it an industrial area? Where's it located? And you'll see reasons why when we get into the planning and stuff like that. Is it a high rise versus a low rise? The high rises are more difficult because we need shafts. We need a lot of outside air coming in and a lot of exhaust air going out. We need room for the equipment that's going to be coming in that's for the lab. You have a lot of support equipment, autoclaves, refrigerators, freezers, the hoods, everything like that. What do we have on the roof? Is there room on the roof for more equipment? Another thing you need to look at is the chemical storage. So flammable chemicals and chemical storage, the higher you go up in a building, the lower the amount of chemicals you can have in the building. So on some of these high rises, we'll look at a bulk storage in the lower level of the building, and then they'll transport up smaller quantities to the labs for usage. Property adjacencies. Are you right next door to another building? In other words, are you sandwiched between two buildings and they're touching you, or is there space between there? What is the setback? What's how close are you to your neighbors? All right, there's an issue with noise. There's an issue with exhaust. What zoning setbacks do you have? What are the restrictions for noise at the property line? Is your property line the center of the street or the edge of the building where it touches the sidewalk? All of these we have to go through. What are our exhaust restrictions? So if I have adjacent buildings and they're taller than mine, or is my exhaust going to affect theirs? And then the construction type. Do we have a flex office? Was it a dense pack office? Was it a data center? We have a bunch of them that were data centers or telcos that had a larger, robust power system and stronger floor system. So those are the types of buildings that lend themselves very well to this. What code changes are going to apply? So I have an office building now, I'm going to be putting a lab in it. Is it going to change my codes? Those are the things that we go through in the early stages of looking at the buildings. On the due diligence side, when we go out to the building, we want to look at the utilities. So we're going to be looking at your power, water, sewer, gas. So on the mechanical side, do we have chilled water? Do we have condenser water? How are we doing our cooling? How are we doing our heating? Do we have boilers? Do we have city steam available on site, or are we going to be putting in boilers? The ventilation exhaust systems, what's there now? What can I put in? Again, what's on the roof? What do I have space for? On the power, what is available in the building, and can the service be upgraded? Because the mechanical systems drive a lot more power. The lab spaces drive a lot more power. So we need possibly to upgrade the service to the building, and will we be able to do that? Does the building have emergency power? Now, a lot of buildings will have a small life safety generator. That's different from emergency power that's going to be running major equipment. We need to keep the exhaust fans and the makeup air running for hoods and for animals and different lab scenarios. So we got to put that equipment on a generator. Now, it's not a life safety generator, it's a standby emergency generator. It's different. If you have a large life safety generator, then we're taking a breaker off of that and putting in a separate transfer switch to feed that equipment. So we have our life safety and we have our legal standby. We want to evaluate the type of lab based on lab and office mix. So how much lab's going to be, how much support office? Is it going to be 50-50? Is it going to be 30% lab, 70% office, vice versa? Those are the things we have to start looking at early on when we go through it. The wind wake. Wind wake is very important because we're going to be doing a lot of exhausting, and we want to know how is that exhaust affecting our neighbors so that we don't get a lawsuit, or the client doesn't get a lawsuit, that these hazardous or noxious odors are being pulled into other buildings. So we would always recommend that a wind wake analysis be provided, and usually it's a specialty consultant that gets hired and brought onto the team. Same thing with acoustics. This equipment makes noise. It's going to be on the roof. It's going to be exhausting either out the windows or off through the roof. We want to make sure that we have addressed acoustics. And that's not only outside the building, but it's also inside the building, because some of the equipment in the labs makes noise too. And it could be next to sensitive offices, stuff like that. You're looking at your equipment space planning and pathways. There's a lot of lab equipment and a lot of need for the MEP equipment to support that. So we have ductwork, we have a lot of piping, we have bottled gases are going to come in, we have chemicals and chemical storage that's going to come in. So you need to think about how am I getting these up and down throughout the building. So if I got a 4-story building without an elevator, that could be an issue. If I have to be able to bring materials up and down, and those are the things to think about. Where are we going to start looking for equipment spaces and pathways? Structural framing. So the floor loading is a big one here, and the ability to support the equipment that I mentioned. A lot of ductwork and pipes being hung from that, and Steve will talk more about structures. Your floor-to-floor heights. So there are some recommendations as far as minimums, and Scott will get into that in our benchmarks or our metrics, and talk about all of that ductwork. All right, so we got your supply air, you got your exhaust air, we have our return air, and you've got a lot of ductwork that's in there, and it's got to fit within the floor-to-floor height. So you'll see some metrics of what we're looking for in order to make those fit. And a lot of times, some of the labs are not going to have ceilings, or they're going to have low ceilings, depending on the height of the building. So we'll talk about that a little more in the metrics. And the type of slab on the floor-to-floor. We'll show you a picture, actually in the top picture here, that is a flat slab. It's a two-way construction flat slab where you have these concrete columns and haunches, and then the floor is flat. The deck is flat. You'll see other ones that Steve are going to show with steel beams and waffle construction and so forth. So what is my actual construction? What do I have to play with and deal with? Okay, and then last, deliveries. So I'm sorry, go back one. Deliveries. You know, do I have a loading dock? Do I have access for trucks? Do I have access for all of the equipment that's going to come in? Because you're going to have bottled delivery gases being delivered. You're going to have a lot of equipment that's going to get shipped into the building, a lot of product going out of the building, but also think about vivariums. So a lot of times vivariums, you want to have a separate pathway for the animals to be brought in and out of the building. So it's a dedicated pathway due to allergens and pathogens, stuff like that, or contagions from the animal. And you want to keep the animal safe, but you also don't want to get anything from the animal to the people as you're bringing them in and out. All right, thanks.
So as Chuck mentioned, I'll expand on the structural component within these projects, you know, the actual bones of the building. You know, if we're starting out with office space, then the building is likely steel framed, especially if it's a fairly recent property built within the last 30 years. You know, however, because we may repurpose a lot of buildings over the last 100 years, then we find ourselves in these different construction types, which can have different levels of drama when we're trying to modify them. Yeah, in terms of what's important when converting to lab space, the two biggest scope items that affect the structure are the building's ability to support the weight of the infrastructure, as well as opening up the floors and walls, which can include a significant amount of chopping. You know, also number two, the vibration performance of the floors can vary between these construction types. This is important because a developer may want to sell their space as having stiff enough floors to not disrupt the tenant's lab activities. So without going into detail, this table is set up to describe how well these systems work for each type of building system, well, with A being the best and requiring likely the least amount of cost, and F being the worst and requiring a significant amount of reinforcing. I won't run into the detail on each one, but generally conventional steel usually proves as the best. This is what we would design a new spec lab building today. When we go back into the 70s and 80s, it's not uncommon to see open web joist framed systems, which have their own issues. You know, they were generally designed cheaply, and the floors don't have, you know, a lot of mass to absorb the vibrations. Then when you go into the pre-60s and 50s, you know, there's still a good crop of buildings out there that were built fairly robustly to be able to support these lab spaces.
Okay, I'm going to take us through the metrics. And essentially what we're going to be looking at here are, I'll say, typical parameters for a laboratory space. And on the next page, we're going to look at clean lab / clean room type spaces, low level clean rooms, and also vivariums. And we're going to compare them against your typical office, just kind of accentuate the major differences that we're faced with when we're looking at a conversion. As Chuck mentioned, some of these are your averages or preferred, but you know, they will vary depending on the actual program requirements that your clients dictate. So to start off, the first noticeable one is the marked increase in outside air required and exhaust. You can see your fractional CFM per square foot for an office, where we're going to be ranging between 1 and 2 CFM per square foot for a general laboratory space. And the range is going to be predicated upon the type of lab space you're maybe considering. A chemistry, heavy fume hood type lab is going to be more on the 2 2 CFM per square foot range, whereas a bio type lab where you have less fume hoods or even no fume hoods, maybe dealing mainly with biosafety chemists that recirculate airflow, you'd be looking at 1 CFM to 1.25 CFM per square foot. And we are noticing geographical differences up and down the, I'll say the Mid-Atlantic East Corridor here, mainly from Washington, D.C. up to Boston. We're seeing a little more in the Boston area. We're seeing more towards the 2 CFM per square foot range, and D.C. and Philadelphia right now we're seeing more in the lower end, between 1.5 CFM per square foot. Normal power, it's about a 3-fold increase from a typical office for a typical lab, and pushing us up to 15 watts per square foot. And this is for really lights and bench equipment. HVAC's loads are going to be on top of that as well. So again, you're just seeing a marked increase just for electrical power distribution within the labs themselves. Also, we see the introduction of standby power. Typical office, you may not have standby power, really maybe just have life safety. In a lab environment, we're going to need standby power, and it's roughly about 1/3 of the total load. And that's to accommodate for anything deemed necessary by the scientists that are critical special. It could represent refrigerators that are holding tissue samples that take months to develop. Essentially what they're trying to do here is protect an investment. They spend a lot of time and effort coming up with a particular tissue, maybe they've been studying for years or months, sorry. It could also be power to a piece of critical equipment that if it stops midstream, if there's a power outage, it would invalidate what it was analyzing, maybe destroying, again, a sample that was being tested, and therefore, again, a significant impact to cost of, again, the science that they've been developing for months. So they may power individual pieces of equipment, refrigerator, freezers, but essentially it's just to allow power for that use. For fire protection, there is a slight uptick in the hazard classification, but essentially it's about the same. Maybe the density goes up in particular areas, so you may have additional heads, but overall, it's really not a big impact to the fire protection systems. We do see a need for additional shaft space, roughly on the order of magnitude of 6 to 8 square feet per floor, and that's really just to accommodate outside air supply and exhaust. Here, the next one we're looking at the floor-to-floor heights. So a typical office, you may find about 12.5 feet floor-to-floor. With a lab, the preference is 14.5 feet, but we can make lower floor-to-floor heights work. It just means a couple different impacts, and it could be something as just the ceiling areas are congested, or maybe you elect to do a exposed ceiling type layout, trying to maximize the clear height. Another avenue might be to develop what I'll call horizontal mechanical spaces. So essentially they may run parallel to the labs, and within these spaces we route the mechanical electrical conduit, the electrical conduit, the mechanical piping, the plumbing process piping such as compressed air, lab vac, and you'd also have your VAV boxes located so that you're minimizing the amount of ductwork that you actually put into the ceiling cavity to just really be the branch runouts to your diffusers. And we have a picture we can show you near the end of the presentation to kind of show you what's been done in the past. But essentially the downside to that is you're going to use rentable floor space, if you're dealing with a landlord or tenant situation, but you'll end up consuming usable floor space for these mechanical areas. So obviously a less efficient gross to net square foot layout, but there are techniques that can be employed to handle lower floor to floor heights. And then Steve, if you wouldn't mind commenting on the structural elements here at the bottom.
Yeah, so for an office space, the code minimum live load requirement is 50 pounds a square foot. However, what we've experienced, half the actual office buildings out there are designed to 100 pounds a square foot, and the other half are really down to this code minimum, 50 pounds a square feet. And then when you're moving over to lab, the code minimum again is 60 pounds a square feet, which is a small difference. But if you're doing a new lab today, you're going to really want to do it for 100, maybe even 125 pounds a square feet. of floor capacity, just to catch any, heavy localized equipment that's going in the space. And so if we're dealing with code minimums, how we make up the difference is there's a partition allowance of 15 pounds a square foot that we can pull from to get the floor up to par without having to reinforce it. And for vibrations, this gives you an idea of the difference between an office requirement and if you want to go for a VCA, which is the minimum vibration requirement for a lab. VCA pretty much handles, bench microscopes and items like that, but it's almost a factor of 6, or sorry, 8 between the two. So if you need a blanket, that vibration performance over the whole floor, it can add a significant amount of cost to upgrade it. So what we've seen is we'll look at the equipment that's actually going in the space and locally reinforce the floor at those areas.
And one other quick note to add for the vibration, in addition to or instead of maybe structural enhancements, the scientists themselves may be able to assist with anything that's vibration sensitive on their part. Essentially, this would only really work for benchtop equipment, but they maybe utilize what's called an air table, and essentially it's nothing more than a small air hockey table that kind of sits on top of the bench, creates a bed of air, and then their sensitive equipment sits on top of that. And then that will basically eliminate vibrations that may impact their sensitive equipment. So again, just to share a thought is even just dialogue with the client may be able to come up with a solution that doesn't require a lot of extra reinforcing. Again, it's really going to go back to sensitivity of the equipment. Okay, next slide. Okay, next we're going to look at clean spaces and vivarium in comparison. And when we're looking at clean space, we're really talking about a clean lab or a very low, the low level clean room, ISO 8, ISO 9, which under the old federal standard was class 100,000. So it's, your very entry level, introductory level type clean spaces. And for the outside air and exhaust air content, it's and even minimal power as well, pretty much equal to a lab. The difference comes in with the clean spaces is they'll have a higher air change rate of air that has to be moved through, through the space, but it doesn't have to be 100% outside air. It can be recirculated air. So at about 20 air changes, we're looking at roughly 3 CFM per square foot. So essentially the outside air of 1 to 2 CFM is fed into the recirculating unit that will serve the particular clean spaces, which will then circulate 3 CFM per square foot. The one key to note, though, is it becomes critical where you locate your mechanical equipment serving these clean spaces. These, I'll call them these terminal end units. Essentially, you want to locate them very near or adjacent to these clean spaces because they are moving a higher volume of airflow than the 1 to 2 CFM I'm noting here for supply and exhaust or outside air and exhaust. Because they're moving roughly 3 CFM per square foot, ideally you want to keep them on the same floor to avoid having to increase your shaft space. Because as I note below, if we're keeping with the 1 to 2 CFM per square foot for outside air and moving that up and down the building, again, you're only needing 6 to 8 square feet per floor of shaft space. But if you're trying to move your clean space up and down, your clean room air, then that's going to increase, at least 3 times that. So just something to be mindful of. The standby power requirement for a clean space goes up, as you can see here, and that's more to deal with just the fact that once you're in a clean environment, the law averages are telling us that, okay, you're going to have more critical equipment, so you just need more standby power available for those uses. In addition to that, it's also good to note that with clean spaces too, the HVAC systems want to be on standby power. With a lab environment, there are avenues where you just would run at a very low load just to maintain pressurization. When you're dealing with a clean space, now you're looking at potential not just maintaining pressurization, but also temperature and humidity. Essentially, depending on how the room is validated, they may need to hold temperature humidity even during a power outage. So again, just things to note when you're doing the programming phase, but to fully understand what their needs are. But it's something you have to deal with, and again, a potential of additional extra power for the HVAC to operate in a either reduced or full capacity. Fire protection, similar to a lab environment, no change. I mentioned the shaft space. The floor-to-floor height, again, you can see our preferences for 16 feet, but again, things can be done to work with lower floor-to-floor heights. And a common technique we've ourselves have done in the past is, if you're taking a typical office building, I've got 2 floors I'm working with in particular. They have a low floor-to-floor, say 12 and a half. It is possible to utilize the space above the clean room area. So if we use the bottom floor for the clean room, we can use the floor above it as a mezzanine MEP type space where we can fit all this equipment. You know, similar to the horizontal chase concept, the downside is it will eat up available rentable floor space. So again, it's a trade-off, but at the same token, you are able to get a clean space into a low floor-to-floor height. So it's, again, trading off your needs and the available space you have to work with and what the program dictates. So it's more of a trade-off. Looking at vivarium, they are similar to your typical lab from what we're seeing. Again, a range about 1 to 2.5. A little higher than your typical lab, and the range is going to be predicated upon the type of animals housed. So if you're looking at, say, swine or canine, you're going to be on the larger end, the 2.5 CFM per square foot. If you're dealing with rodents and racks and individual cages, you could be on the lower end. More so if you're utilizing ventilated racks for the rodents as well, because in the case where you have ventilated racks, you know, your typical room might be, say, an air change rate anywhere between 8, and I've seen them as high as 15 air changes. And again, that's for odor control in the situation. But if you have ventilated racks, that required high air change rate is really isolated to just the racks themselves. So you can have a significant decrease in air. And sometimes in projects we've done in the past, we'll run the room at, say, 6 air changes instead of 8 to 15, because the racks themselves, since they're ventilated, they're containing the odors, and again, it maintains a nice air change rate within the rack itself, you know, much higher than 6 air changes, because of the volume of those racks are much smaller. So again, something to think about when you're in the programming phase to understand what the client might be utilizing as far as type of housing cages. On normal power, we have a pretty wide range here. Your typical wattage per square foot, and this is really not going to be for the holding areas. It's really going to be for your support areas, such as necropsy, surgery, or cage wash, and more importantly, cage wash. And hence, that's why we're throwing the 30-watt number out. Cage wash tends to use steam. Therefore, in a type of lab conversion, if you don't have gas or natural gas or steam available, you're forced into using electricity to generate steam, and that's where you get the higher number from. Tremendous amount of energy needed, and if you're forced into utilizing electrical power, you're going to be closer to the 30-watt per square foot range. Standby power, increase similar to a clean space requirement, but also the note here, it's more paramount to keeping the animal safe. You know, 2 main entities, boards that kind of guideline how the animals are treated are ALAC and NIH, and they advocate, you know, the well-being of the animals. And it's important to maintain temperature relative humidity at all times, not just for the comfort of the animals, but it could also have an impact on the science. If the animals are stressed, that could lead to impacts to the studies being done or being conducted. So it could basically damage months of research. So again, it's paramount to the scientists to maintain the comfort level of the animals. Fire protection wise, we're, again, similar to a typical lab, same thing with the shaft space. And since we are similar to a typical lab, we're back down to the 14.5 floor-to-floor height preference. But again, there are techniques we could do similar to what I've mentioned for labs and clean rooms of how we could deal with vivarium in a similar space. And then Steve had noted before about the floor loading. It's similar again here. The only thing I want to highlight addition is especially with vivarium, the animals are very sensitive vibrations. So it's paramount that the areas designated for housing receive that care. So back to what Steve had mentioned, potentially you might have to maybe strengthen the structural bays beneath the animal holding areas. But again, it could be restricted to just the vibration sensitive areas. Okay, next slide. Okay, next Chuck and I are going to talk about planning, how we would maybe execute these types of conversions. And I'll start off. So, you know, kind of alluded to this in the metrics. It's really paramount to understand your programming needs. And to start off is, what type of lab are we looking at? Is it chemistry, biology? Is it a landlord-tenant situation where it'll be incubator hoteling, where you're looking at individual labs maybe rented out or leased out, or even benches, linear feet of benches? It's important to understand that in the sense that it will impact maybe how some of the central utilities are laid out. You know, is it just a spec lab? Do you have an anchor client where they may be taking over a floor or the entire area? Because obviously, if you're dealing with an anchor type client, you'll have a lot more direction exactly what their needs are. When you're looking at incubator or spec, you're now applying maybe averages to the industry to your designs. So you're trying to be more accommodating, more flexible than say maybe an anchor tenant might require. And then specialty spaces, as we were just talking, when you start hitting vivarium or types of clean rooms, it's important to know versus say your general lab space. Other thing to keep in mind too is chemical storage or even chemical usage. You know, again, the codes dictate how chemicals can be stored in known quantities for the, you know, based on the flammable requirements. As far as amount allowed per floor, as well as your control zone. So just to kind of simplify, you know, we're not going to go into detail, but just to simplify, the lower you are in a building, closer to the ground, the more chemical that can be stored individually on each floor, each control zones. You get more control zones available. And that all dictates basically how much volume of chemical you can store. As you go up a building, it gets less and less. Now, in those situations where you might be dealing with a situation where you need to occupy higher levels, there are, again, abilities to designate a chemical storage area on the lower level that say maybe is shared. If again, we're looking at a leased laboratory that has a lot of different tenants. So you could still have the bulk of your storage down low, but of course, when you do something like that, you got to make sure you have the avenues to move the chemical up and down the building, especially if you're doing a mixed use facility. You want to keep the movement of chemicals separate from the movement of people. So you would just want to make sure you have a you know, path movements to the building, as well as even possibly a separate elevator. You know, typically a freight elevator will double. It's not just freight, but also can be utilized for movement of chemicals, say, which would then allow you to keep it separate from people. The other things we look at is, again, the types of utilities we need: equipment space, shaft space, louver, and roof space. So really just looking at all the spatial requirements needed. You know, as I mentioned earlier about the type, the roughly 6 to 8 square feet per floor requirement for shaft space. You really just want to plan out that how you're moving the ductwork up and down the building. You know, assuming you'd have your supply and exhaust separated, because there are code reasons for the exhaust that needs to be in a separate fire rated assembly or at least subduct configuration. Because it's deemed hazardous exhaust, you cannot put fire dampers in it. So there are some situations you have to deal with that maybe you know, again, you wouldn't have in a typical office, but a couple of different impacts because of the fact that it's a lab application. As Chuck,
So Scott, on the,
yeah, sure, go ahead, Chuck.
on the, you know, when we have it, how much infrastructure do you want us to provide? This is the question that we have to find out up front. Is the developer building this as Scott mentioned the types, but is he doing it just for the core and shell, or is he doing the full fit out? So are we bringing the utilities, sizing the chillers and the boilers, whatever it is, getting utilities to the space and stopping, and then the tenant picks it up? The tenant puts additional equipment on it. So for example, it could be a condenser water system, and we bring the condenser water down, the tenant puts pumps on it, they put their own water cooled DX equipment on it, all of this stuff. What the delineation of core and shell and tenant is important to know here, because the developer is paying for what we install is in the core and shell. So looking at the utilities, we also want to know, you got a building that's got 1 million square feet. How much of this can I make labs in office? Well, we need to do breakpoints. And the breakpoint analysis goes through and evaluates what's the power that's there. We take the metrics that Scott was talking about based on the types of lab, and we apply them to those to what's available for the incoming service, both electric, gas, water, sanitary, and then we look at the mechanical equipment too. So what's already there, chiller wise, rooftop wise, and you start evaluating, okay, if I go to labs of 100,000 square feet, a lab with a complement of office, what does that mean power utilities wise? Am I still within what's in the building's capacity? And as I go up in quantity of lab space, I hit a break point. I need to put another service in, or I need to put in more boilers, or I need to put in more chillers, or the water service isn't large enough. So you have to go through the breakpoint analysis to identify how much lab can I put in this building. Brand new, it's an existing building, it's 50% unoccupied, how much of it can I convert over? And then what's that price point to do that? So all of this is part of the analysis. The equipment space, whether it's on the roof, we have to evaluate that, our clearances for airflows, whether it's on the floors, this is all part of the evaluation. Scott's talking about makeup air and exhaust air and our standby power. Someone put in the chat, the wind wake analysis, they were asking what that is. So that is an electronic model that they do. And sometimes they use a physical model and put it in a wind tunnel, but it is depicting the standard airflows around the building with prevailing winds and other adjacent buildings to see where the air is going to go. So it's an analysis or a tool, kind of like computational fluid dynamics, CFD, to see how your exhaust is going to impact the neighbors, where it's going to go. So it's an actual computer model. But like I said, we've had some clients that will build a physical model and put it in a wind tunnel, and they have to do it based on taking air samples and air path samples around the building to find out what is the typical airflow pattern based on adjacencies in other buildings. And then you get into the specialty systems, the enhanced systems. Are we going to be putting in localized or centralized vacuum? Same thing with compressed air, purified water. Are we looking this for injection? Are we looking this for DI water, for cleaning of equipment? And we're probably going to have acid neutralization. A lot of times that's put in as a central system, and then each of the tenants tie into that central system. So those are the kinds of things that we look at for what's the programming required, what is the developer or the landlord or the tenant or the project require, and we identify what the breakpoints are so we can move forward.
And then Chuck, just to add to that, with the enhanced systems, it will come down to the type of lab we're laying out. So if you're, say we have an anchor client where they're taking a large, if not all this space, these enhanced plumbing systems may go in because again, they control everything. But if we're dealing with, in some cases, when we're dealing with a more varied tenant space where there's a lot more tenants available, these types of enhanced systems may be pushed onto the tenant for them to provide their own. And it maybe with the pH neutralization, the waste neutralization, there might be common riser stacks for them to dump in their treated waste, but the actual treatment system would fall onto the tenant. And if you go further, when we go even into an incubator type setup, it actually may be a driver to bring them back into the project or into the I'll call it the landlord system side or the core shell. The reason being is that when you're dealing with an incubator setup, the tenants themselves tend to be more of a very startup type level, and they just don't have the capital to put their own systems in. So in these situations, those types of clients or tenants are looking for a landlord that can actually provide these services for them, and they're willing to then pay, on a per square foot basis for use of them. So again, it goes back to understanding the type of tenant that may be occupying the space. Okay, next slide. And then back to you, Chuck.
So this is the concept of what's on our roof and how do we go and fit more stuff on our roof. So we're physically looking at, and we take our drawings and show the actual size of the equipment that we need to put in there based on the different breakpoints, and go through the entire layout of the building as far as the roof is concerned for our additional equipment. This is actually plays into the next slide, which is Boston's 451D Street. This is the roof for this building. So in this case study, 451D Street is a finished project in Boston that we did. That was the roof for it. So this building is physically two buildings butted together, all right? And they're different heights because they're different floor structures. So One's got a terracotta floor structure, which is 11.6 slab to slab, or the other side is cast in place concrete, which is 12.7. So the floors did not align. So that was a challenge. But it used to be a telecom service provider. So it had a lot of power, and it actually had high pressure gas, which is unusual. So the service was a 13.8 kV service. It had three 4,000 amp, 480 volt double-ended switchboards and over 40 watts a square foot of power. So it fell well within the metrics that Scott was showing you. We added two 300-ton gas-fired DX-cooled rooftop units to support the labs with makeup air. And there's a strobic array, which you may see in the next slide. There's a strobic array on the roof for the exhaust. And we use the strobic type fans. There's other manufacturers similar. It induces the air from the outside of the building into it to give us a larger air quantity and higher plume. So we get our velocity that we need, and we get it up and away from the building. We also have in this project a glycol heat recovery coil. It goes between the supply and the exhaust air. And that was for energy recovery. And like I said, we used the abandoned shafts on the right-hand side of that picture of the circle. That's one of the telecom shafts. So we utilized some of those for our ductwork and our risers within the building. They were handy to use for getting our components up and down throughout the building. The services for the labs were in various locations on the floor. The whole building was not vacant. There were existing tenants. So we had to piece together the lab spaces and the utilities for the lab spaces within this. It was a historical building that always gives you a challenge. And if you go, you can see here, it's almost 500,000 square feet, 9 stories plus a basement. It took up the entire city block, long, skinny, 2 buildings connected. If you go to the next slide. So there's the picture of the strobic fans upper left. They look like stormtroopers. So what they do is they actually induce air and include that with your exhaust from the building, and it shoots it up high. You have a redundant fan too. So you always want to make sure you have a redundant fan in case one goes down so you can maintain your exhausts. Although the building was 500,000 square feet, we've converted 150,000 of it to lab space throughout the whole 9 floors. And we had to do a central chemical storage as well. So the lab office mix-up was about 50%. Our lab makeup air and exhaust air is about 1.5 CFM per square foot. And as you can see, we had plenty of power there for normal and standby, and we had 2 neutralization rooms because the building was so long. If you look in the picture on the right, you can see there's red ductwork coming down. So again, it was not every floor had labs. So we had to be able to get the ductwork to the spaces that were going to become labs. So this is an alley side, and they ran the ductwork down and they painted it to match the brick. From an engineering standpoint, we love that, but I know architects don't. If you look in the lower left, you're going to see the large air handler. And what helped in this was they ran the ductwork across the roof to get to the different shafts to be able to go down. So it didn't eat up a whole floor, because that ductwork is huge, as you can see. Okay, next slide.
Okay, I'm gonna run into this case study, but real quick, Steve, did you have, I thought you might have had some work on the Boston job. Do you want to talk anything about the structure on that one real quick?
Yeah, the quick takeaway for that one, as Chuck mentioned, half the building was terracotta floors. They're spanning 15 feet arched systems, and we did an investigation on them. And the takeaway is, you can't rule out those old buildings. The original usage for that structure was it stored military equipment back in the day. And after we did the investigation, we found out that terracotta itself had plenty of capacity, had upwards of 200 pounds a square foot. And it was also good for vibrations as well. It's just going back to the table I presented earlier, it's really tough to chop up terracotta. It's a very brittle element, and it's really tough to put openings in the floor slabs with. So that's really the takeaway for 451D on that.
Okay, thanks, Steve. All right, I'm going to talk about one we're doing in the Philadelphia region. This is this current project's in design. We just issued some pre-purchase work, but we're still working out the final design. And essentially, it's a large high-rise, 29 stories, 730,000 square foot building. We're going to take up a portion of it. I'll show you that on the next slide. As Chuck mentioned, we did a study for this particular project and kind of backed into what we could work with. We looked at the power, and we did have sufficient power. mainly because a couple floors were dedicated to a data center type client that has now since vacated. So there was already power available. There's also a high pressure gas service that runs by the building and is tapped into already. So we have access to that. And then, there are multiple telecom entrances, so to help with just as far as how we would wire up the space. In addition, essentially what we looked at was everything that would work from an MEP standpoint. And in the end, we ended up settling on establishing the maximum amount of airflow that we could get from exhaust. The picture you see here is a sketch we had done in Bluebeam. And in blue is actually the strobic type fan, similar to what Chuck showed for the last case study. And we essentially were able to basically fit on the smaller roof where we're locating the fan, essentially up to 80,000 CFM. So that now became our limit. And then we looked at applying a 1 CFM per square foot, which then backed that into a biological type setting. Hence, we had 80,000 square feet of lab space that we could work with. And essentially that all came out in a facility study that we've done. And then, we took it further from there. And just a real quick note too, the building itself, we're dealing with, it ranges between 13 and 14 feet floor to floor, but we do have a couple areas where we've extremely deep girders. So we're working with that. The other thing that was helpful as we're continuing to design is some of these deep girders have already pre-engineered notches put in them when the building was originally made. So we're making use of that to try to minimize how low the ductwork has to sit. Okay, next slide. So in the end, as I mentioned, we came up with the 80,000 CFM limitation, which is an 80,000 square foot limitation based on that 1 CFM per square foot. So we're roughly looking to convert about 120,000 square feet. So it's going to be a mixture of lab and office within this total framework of area. And we're also looking at locating the labs on the lower floors, essentially 2 through 8. And that goes back to my previous comment about chemical usage. The architect had looked at this with a client and they kind of went through what they're comfortable with storing, the amounts that are going to be limited to, played against this need to put a dedicated space down at the loading dock level. And in the end, they felt they didn't want to do that. They wanted really to allow the individual tenants to be able to bring all the chemicals up to their space. So they opted to keep the development at the lower floors. Excuse me. As mentioned, and when I went through the metrics, we have makeup air, we have lab exhaust that we provided in a core shell environment, a certain amount of standby power available, and then we did create new shaft space. We were not able to use existing shaft space, or as Chuck noted in the last case study, we were not able to utilize an elevator. In some cases, there might be extra elevator space, so the team is able to determine that one of them can be removed and put into use as a shaft. We just didn't have that luxury on this project. Under provisions, overall, they're averaging about 50 to 50, but the first fit out we're looking at, we're definitely a lot higher on the lab to office ratio. So it's going to vary floor by floor. As I mentioned, we're about 1 CFM per square foot on power or airflow. Here, just a quick note, the normal power you can see is a little bit higher than the average. Our average, I said earlier, was 15. This particular job, we are ending up with 20, but thankfully we have that power, so we're able to meet the need. And this 20 right now is predicated on walking through with a lab planner. Essentially, this setup, these labs are basically being deemed incubator, at least the first 2 floors of fit out that we're looking at. So we're dealing with more speculative type space planning, and again, looking for flexibility. They've had some feedback in the lab market, maybe some of the tenants that are interested in the space. So we're utilizing some of that feedback that the developers already been able to garnish from the industry. Standby power is pretty. It's even with the average of about 5 watts per square foot. And one other quick note is the centralized lab waste. We actually were flip-flopping on this project. We were dealing with a developer who was not familiar with actually labs in general, so they were not comfortable managing the these new environments, these new floors that they're going to have within their facility. So originally they were looking to have the tenants take on the lab waste neutralization, but as we talked through and understood that we're going to be doing an incubator environment, it was back to that earlier comment I made where their tenants may not be able to afford these types of systems. So they acknowledged that they would indeed provide this lab waste neutralization system. So you can see there, it jumps back and forth. It's going to again be predicated upon your tenant, your end use requirements. One other quick note on this particular case study, we were fortunate enough to work on the core shell and at least do the first 2 floors of fit out. But it put us in a position where we can we've modeled their airflow in total, and then we've been utilizing it as a sanity check each time we look at fit out requirements and back check against it. So initially, when we're looking at these first 2 floors coming out of the gate, they're originally looking to consume about 40,000 CFM of the total available air. And since we're at 80,000, that meant 2 floors out of 8, we're going to take up 50% of the allotment. So we're able to bring that to their attention, and then we're able to work with them in a lab planner to really focus in on exactly how many fume hoods we needed and other types of requirements that allowed us to reduce that airflow back down. So it was nice to know that we can utilize the infrastructure planning tools and calculations to also help self-check against development of the different floors as they would go up the tower. So that will be something that will be kept into play as they go beyond the initial 2 floors of fit out. Okay, next slide.
So this is another case study from our Boston office. This building is 6th floor office building that we had designed as an office building, and then they decided to change it to lab. So they didn't change the floor to floor height, they just changed how we're going to actually utilize the building, and we had to change the internal and the external, all the MEP systems to make it accommodate that. The building is a long building, 230,000 square feet. And because it was so long, one of the things we had to do is 2 acid neutralization systems because of the length. So you have to run the piping all the way through. And it was a 50-50 lab to office split out. And you can see our normal power is about 7 watts square foot for the office and 15 for the lab. It did fall into the high-rise classification, so we had issues with our shafts and everything, which is what Scott pointed out, got to be separate fire-rated shafts. And we did come up with some custom evaporative cooled rooftop units to provide the makeup space or the makeup air for the labs. I think there might be another slide. And you can see on the roof here, you got your strobic fan array on the top, and on the bottom, this is kind of we'll call it a utility corridor, if you will. So the lab being on the left-hand side, you see the rack of piping that's for the utilities, and then you see the VAV boxes over on the right. Some exhaust, some are supply. And that way, using a piece of the floor for the utility spaces based on the floor-to-floor height not being enough, it is another viable option to identify how you're going to be able to fit everything into a low floor-to-floor height. The one on the right is actually a mezzanine where I believe, Scott, they cut through a hole in a hole in a floor. And so they have 2 floors and they built an interstitial mezzanine for more of the mechanical support spaces up there.
Yeah, that's correct, Chuck. Yeah, that's a picture of there's actually a clean room sitting below this. This was a spec office building that got converted into clean room. And what we're looking at is a picture essentially where I was standing on the catwalk that's directly above the clean space. So, again, as I mentioned, the downside is, okay, this used to be office space and it had to be converted into mechanical. But in this particular case, the one client took the whole entire building. So it just met their needs and they're okay with that. So it wasn't, in a way, it wasn't like they were stealing rentable space. Essentially, they're just stealing it from themselves. But again, it just shows you can put a clean room in an office.
Okay. So some of the lessons learned we want to talk about in the planning stages, we want to make sure that we help the client understand the market, what type of labs are going to put in. Like Scott said, we're working with a developer that wasn't really familiar with them, talking about they're going to be incubator type spaces. Some are anchor, some are different types of lab spaces, vivariums and so forth, and establish, the criteria based on that. Think of things as being, flexible or modular. So you could build the infrastructure to support a multiple build out of lab suites, if you will, but only the first one gets built at day one. And then as you get more tenants, you're connecting into the utilities and continuing down the row. Verify the redundancy requirements, not only on the exhaust, but you got generator, you also have, because you've got a lot of refrigerators and incubators and stuff like that need to have standby power, but the redundancy of the makeup air or the supply air. Okay, well, what do we have to do there? You want to create a clear basis of design, and you want to refer to that basis of design repeatedly, not just for the MEP. This is for the lab planning and for the architecture as well. So you're constantly going back to the multiple stages of the design and following with the BOD or adjusting the BOD if the designs needs change. But it's important to have a clear basis of design that identifies the type of lab and how you're going to approach the lab. And like I said, visit it and refresh it through every phase. Always think about how to be flexible with the system so that they can grow, they can expand, they can add to it, and really dive into the base building infrastructure so you know what is going on structurally, but from an MEP standpoint. We really need to know what is our limitations that Steve walked you through with the floor loading, the full clear floor heights, all of that information, how we can modify the floor. Is it terracotta? Is it going to fall apart? What's going to happen there? And one thing that we found was very helpful is including trade subcontractors with a CM early on in the project. And this is for consideration on, how the material is going to get into the building, how we're going to route it in the building, and coming up with cost analysis along the way. So, hey, if we use this type of material, that's the cost, but it doesn't last as long. You use this type of material, here's the cost. Also look at different system types. We could be doing a custom evaporative cool DX unit on the roof, or we can go to a different type of unit. And what are the ramifications? Cost, performance, longevity. It's very important to be able to do that all along throughout the project early on, so we get the right decisions made for the client moving forward. Okay, next slide. And that is the end. Any other questions besides the Wind Wake one that we saw? I'm not on mute, am I?
Nope, we can hear you.
Any questions? Well, we appreciate everybody attending, and we hope it was insightful and you learned something from it.
Hey, Chuck, we did get one question. Range of, and I'll throw this out to the three of us. Is there a range of prices per square foot for these conversions?
You talking construction costs? I guess you're asking for
construction cost. Yeah, I'm assuming.
That's a good one.
Yeah, I was gonna say off the top of my head, I don't know if we.
Yeah, I don't know off the top of my head either.
we
could get back to you on the ones that we showed here as our case studies, and let you know what they ended up being.
Yeah, I think that would be a good thing to note. We can do that. Get back to everyone. Give and share. I know mine's in progress, so they might be still counting, but I'd be happy to share anything we have, even at an estimate level, I'll call it, since we haven't gone out to bid yet.
And we'll have to clarify the level of the build on those two case studies, whether it was just we did the core and shell and the tenant took over the rest, or what. So we'll try to get you that information.
Yeah, good point. And then keeping in mind too is you'll probably see variations in that, especially with the low floor to floor heights. Your cost should generally go up because you're going to spend more on just the contractors coordinating, trying to get everything to fit.
Right.
But generally speaking, it probably be close to your typical. And I guess what we can do too, we can share difference between lab, cleaning, and vivarium.
Mm-hmm.
Okay.
Any other questions?
One more question.
Yes. So I just saw that. I'll read that one off. So, are the tall, the strobic type exhaust fans loud, and they are. As Chuck mentioned, they actually pull and make up air off the roof. They also have the nozzles themselves that induce airflow, and what they're doing is they're elevating the velocity so the discharge can be projected. But of course, higher velocity will definitely just translate into higher sound. You are able to buy attenuating nozzles that work with it, but they're still loud, compared to your conventional fan. So as Chuck mentioned, it's a good neighbor policy. You want to look at those sound levels, and we mentioned about the wind wake or reentrainment studies. Also recommend bringing on an acoustician to look at that as well, because it gets a little more complicated. You're looking at sound level and generation and the way it's distributed in the air in an open environment. So it's a little more complicated, and it's always good to get the acoustician's opinion on that.
George, the fans are not that loud. You cannot hear them from my house.
We got another question
from George. You want to take that one, Chuck? See it in the chat.
Oh, yeah. So what we're finding in the suburbs, most of ours have been in the urban area. In the suburbs, we're finding that they are looking at converting a lot of the lower 3-story, 1-story buildings. They're actually, some of those buildings have a higher floor-to-floor height. So and they could just be the single stories with a lot. Those are some of them are very well adapted to that. We have some that they're looking at warehouses, converting them over. The only thing we have to do there is we have to get Steve involved, because we need a lot of dunnage on the roof to hold all that equipment that we're showing you up there, because warehouses don't have that kind of roof load. Sometimes the equipment's laid on the ground and ducted up into or piped into the building. We've seen that as well. But yeah, this is a push. We're seeing this push not only in the urban areas, but the suburban areas as well.
Yeah, to add to that, the clean room we looked at earlier on the last slide there, that was a 2-story office building in a suburb type environment. And then as Chuck just mentioned, I can say, yeah, we're looking at a particular project at the moment where it is a warehouse space, and we're doing exactly that. We're looking to actually put the equipment on grade as opposed to putting it on the roof, because the roof is your typical low load, warehouse type structure. So it's not even worth probably upgrading. And since we have the benefit of what we're looking at in this warehouse space is going to be it's quasi-production type area. So we don't have to worry about trying to stack another floor inside the warehouse. So we got a lot more room to work with. So we can come up the side of the building and in. And because also it's a warehouse, we're in an industrial park. So, as far as the aesthetics go, less of a concern than say if we were in a suburb type environment. So we got a little more flexibility with that type of space. And just knowing it's in an industrial park, it's given us a little more latitude.
One thing you find with the suburban type buildings, with the 2- and 3-story buildings, they're typically got a larger parking area around them, which separates them from their neighbors, which also makes it better for wind wake and any cross contaminants and noise. So your buildings are more further apart.
Good point.
Okay.
All right, if there's no more questions, just want to thank everyone from Bala and everyone else for joining this. And of course, Clemens looks forward to teaming up with Bala in the future to complete some of these projects together. So thanks again, everyone, for joining.
All right. Thank you, guys. Thanks to everyone.
Yeah, thank you.